Okay, let's continue our function and the graphs. And we're going to concentrate on section 1.5. We learn how to analyze the graph of functions. So first, learning objective using the vertical line test function to determine the function. Second one, find the zeros of the function. We will learn how to determine a increasing interval, decreasing intervals, or increasing function, decreasing function, determine relative maximum and relative minimum. And we also will learn how to determine the average rate of change for any given function, and also how to determine the even and odd functions. So first of all, we look at the graph of function. So, graph of function basically is determined by order pairs. So graphically speaking, we come up with order pairs. And second one, just connect those order pairs. Connect them with a smooth graph. Smooth curve. Okay. So graph of function is collection of order pairs. Order pair basically come from x, y, and we're using the function notation given x value and the y value will be f of x using the function notation. As you can see, the x-coordinate is the direct distance from the y-axis and the point. So, yeah. And then if you transform that to become the horizontal axis right here. Okay. And the y-coordinate is the direct distance from the point to the x-axis. So this becomes the y-coordinate. Y-coordinate is the same thing as f of x. Now let's find a domain range of the function given in the graphical form. Now let's take a look at this. Function itself is not given, but we are given the graph of the function. So first of all, we determine the domain. Quick review: domain are all possible x values. Let's take a look at what x values are possible here. And there's endpoints here, so we get a left endpoint. This point is what we call the left endpoint. We also have a right endpoint. And this two endpoint determines the boundary of the graph. Also give us the clear idea of the domain range. So domain start with the -1 on the left and all the way to 5. We are including -1 but not 5. So domain here should be -1 all the way to 5, including -1 but excluding 5 because there are open circle here. Right endpoint is open circle. Open circle indicates we're not including that point. So the x-coordinate is not part of the domain. And we want to also find out the function values of -1, meaning here x equal to -1. So go here, x equal to -1, y value equal to 1. Okay, so f -1 equal to 1. f2, when x value equal to 2, we have this point right here. And then the y value turned out to be -3. Okay, so f2 equal -3. Now let's take a look at range. Again, range was determined by the lowest point and the highest point. Right here, this is the lowest point. can also call that the minima, right? The absolute minimum, lowest point. We also have a highest point. And these 2 points determines the range. So start with -3 all the way to 3. And we are including both because both lowest points and highest points are solid points. So range here are all possible y values. And the range should be, in this case, from -3 to 3, including both endpoints. As you can see, those endpoints, left endpoint, right endpoint determines the boundary here, and the graph doesn't go beyond those 2 points. Okay, so we're having a limited graph, do not extend in both directions. And if you look at it, since for any given function we have a one-to-one relationship, one-to-one, meaning one y values corresponds with a given x values, or one x value corresponds to one y values. That means for any given x coordinate, you can only have one corresponding y coordinate, not 2, not 3. So that's exactly the definition of the one-to-one relation. So that means if you draw a vertical line, you can only intercept the graph of function most once. A very important guideline. So let's say you draw a graph, any graph. Okay, and then you draw the vertical line. Let's say you have one intercept and most one intercept, right? Let's say if the graph stops here, and you can draw a vertical line here, has no intercept, because the graph doesn't extend beyond that, the right endpoint. So that's why it's called at most one. So vertical line can only intercept the graph of function at most once. Now let's take a look at the formal definition of the vertical line test. Vertical line test is used to determine a function. Determine a relation, whether a relation is a function or not. Determine a function. So we have such a point in the coordinate plane. The graph of y as a function of x, and then if and only if no vertical line intercepts the graph at more than 1 point, meaning the vertical line can only intercept the graph at most once. Vertical line intercept the graph of the function at most once. Okay, that's the essence of the vertical line test. So I'm just quickly giving you an example. Let's say we have a circle here. If you look at a circle, if you draw the vertical line, you're going to have 2 intercepts. Okay, so that's definitely not a. So if you draw any 2, you have 2 intercepts here. So this is not a function. It's a relation, but not a function. Also, you can look at something like this. Okay. Again, if you draw the vertical line, you're gonna have 2 intercepts here. One here, one below it. Okay. So again, this is not a function. Okay, so vertical line test will give us a quick, determination of a function. And let's take a look at zeros of the function. Zeros is also called the x-intercept of the function. if you want to find the x-intercept, you're setting y equal to 0, y or f of x equal to 0, and solve for x. Okay. So zeros of the function is determined by this standard procedure. X-intercept typically using a comma 0, so y value is always 0. That's guiding principle. So zeros are a function of f of x. We're setting f of x equal to 0 and solve for step 1, set f of x equals 0. Step 2, solve for x. Step 3, list all the zeros. List all zeros. Zeros is also called x-intercept. Okay. Now let's find zeros of following functions. Okay. A, we are given f of x equals 3x squared plus x minus 10. We're going to find the x-intercept of zeros. So setting f of x equals 0 first. That means 3x squared plus x minus 10 equal to 0. So we go factor this trinomial 3x x. And right here, we're gonna need a positive 2 here, and 5 here. The reason why is because we want to come up with this particular result at breaking down the first leading term 3x and x. And I'm going to break down the last constant -10. There's a couple ways of breaking down that, and we won't guarantee that we're going to end up with a middle term. So what we can do is put -5 here, put positive 2 here. -5 times positive 2 is -10. 3x times x is 3x squared. Now we cross multiply, and 3x times 2 is 6x minus 5x, so cross multiplying, end up with a positive x. And that matches the middle term, so guarantee of the returns. Now we come out with the proper factoring. 3x minus 5 goes into the first parenthesis, x plus 2 goes into the second parenthesis. Now you can solve for x for each linear equation. First one, adding 5, you get 3x equal to 5. Now we divide 3 from both sides of the equation, so we end up with x equal to 5/3 for 0. Second one, subtract 2 from both sides of the equation, x equal -2. So basically we have two x-intercept here for first function, 2 zeros. First one is 5/3 0. Second one is -2 0. For the first function. And for the second function, we get a g of x. Let's go back a little bit. So as you can see, if you graph it, you can easily find this both intercepts right here. One of them is here, the other one is on the right. This particular parabola, and this parabola opens upward. I have a couple x-intercepts. Let's take a look at the second one, part B. G of x equal to radical 10 minus x squared. Similarly, we're going to set y value equal to 0. So in this case, y is the same thing as g of x. G of x equals 0. That means radical 10 minus x squared equal to 0. Then we'll be able to solve for x by squaring both sides of the equation first. we get 10 minus x squared equal to 0. Now you're adding x squared from both sides of the equation. Cancel that, switch the order, x squared equal to 10. And we take the radical from both sides of the equation. Radical x squared equal plus minus. When we take in an even root, we always put plus minus on the right hand side. So x equal to plus minus radical 10. So we get a couple zeros or a couple x-intercepts. First one is negative radical 10, 0. And second one is radical 10, 0. Okay. And you can easily go over that, go over the procedure and finding those zeros. As you can see, from the graph, this is actually a half circle. So there are a couple intercepts, one on the left, one on the right. Now let's take a look at the third function, h of t. Notice that we're using different variables from part A all the way to part C. The variable is just an instrument to express the relationship between those two variables. So it doesn't matter what variable you are using here. So similarly, we're setting y value here. This is y value. H of t equal to 0. So that indicates 2t minus 3 over t plus 5. Set that equal to 0. And to the proportion, we can just cross multiply, and we will easily come up with the equation to solve for t. 2t minus 3 times 1 is 2t minus 3. T plus 5 times 0, that's 0. Now we get a linear equation with one variable t. Now we can solve for t. First of all, adding 3 from both sides of the equation. And we get 2t equal to 3. And divide 2 from both sides of the equation, we end up with t equal to 3 over 2. And so therefore, this particular function, we have only one x-intercept, or 0. And that 0 turned out to be 3 over 2 and 0. Okay. You can also verify that easily from the graph. It's only one x-intercept. And if you draw the vertical line test, okay, so if you draw the vertical line, you can easily verify only one intercept, right? Anywhere you draw the vertical line, one intercept. And that indicates it's definitely a function. Okay, this is one-to-one relation among those two variables. Okay. Now let's continue to the increasing, decreasing functions. So typically, if your function is increasing, it will look like this. This is increasing all the way from negative infinity to infinity. Another example could be decreasing all the way. Okay, this is decreasing all the way from negative infinity to infinity, right? It's going downward. This is going upward. Okay. So for increasing and decreasing functions, we have 3 major categories. First one is, look at this graph. We have 3 different categories. First one is decreasing interval. In this case, from -2 to 0. Okay. From -2 to 0. This is definitely a decreasing interval, meaning it's going downward, decreasing. And from 0 to 2, interestingly, from 0 to 2, it remains flat. So remaining flat indicates it's a constant function, or it's a constant interval. doesn't go up or down, so it's constant. And from 2 to 4, in this case, 2 to 4, it's increasing, right? It's going upward. So this is a typical increasing interval here. You can generalize the entire function. That's very practical. But just give you an idea of what a shape look like. So increasing, decreasing constant function. So if you look at, let's take a look at it from an algebra perspective. If it is increasing, let's say this is x1 right here. This is x2. If the function is increasing, meaning x1, when x1 is less than x2, also the y value at, this is f of x1. This is x2, f of x2 is right here. F of x2 is also on top of f of x1, meaning f of x2 is greater than f of x1. That indicates this is the increasing function. So x value and y value have the same direction. That tells us the increasing interval. And then decreasing, similarly, let's say this is x1, this is x2. So x1 is less than x2. And if you look at f of x1, is on top of f of x2. So f of x1 is bigger than f of x2. That means x value and y value have opposite direction. And this is a typical decreasing interval or function. For a constant, let's say this is x1, that's x2. It doesn't go up or down. Although x1 is less than x2. However, f of x1 is equal to f of x2. They are the same. They point at the same, turn out to be the same value. So that means it's a constant interval. So by drawing a quick graph, you'll be able to understand this concept a lot better. Now let's describe this increasing, decreasing, or constant behavior of each of the function. Partly, as you can see, f of x equals x cubed. So it's increasing all the way. Right? If you forward direction here, it's moving upward all the way. Just follow the direction. So this is increasing. Entire function is increasing. So increasing from negative infinity to infinity. And second one is a little bit more interesting. So we have two different types. So it separates into 3 different intervals. First interval from negative infinity all the way to -1. So it's going upward. So that's increasing interval. So from negative infinity to -1. And from -1 to 1, it's going downward. So that's a typical decreasing interval. -1 to 1. Now, from 1 to infinity, it's moving upward again. So we have 2 increasing intervals here. Negative infinity to -1, and then 1 to infinity. 2 type. And then the third one, right here, is piecewise function. We have 3 pieces. First piece from negative infinity to 0, right here, it's increasing line, right? So it's increasing. So increasing interval from negative infinity to 0. And then from 0 to 2, as you can see, it's constant. So we also have constant interval. That's from 0 to 2. From 2 to infinity, it's decreasing. It's decreasing line, so it's going downward. So decreasing interval is from 2 to infinity. And this one has all three different categories of the behavior here. And also, let's take a look at relative minimum and relative maximum, because it has something to do with the increasing, decreasing intervals. So relative minimum, you can also call that value. So that means, let's say, function decrease all the way to the bottom of the valley and then start to pick up to increase. This is what we call valley. Let's say this is A. And so for x value between x1 and x2, let's say this is x1, this is x2, A is between x1 and x2. And you can say x equal to A. Then at this particular at the point of the valley, or the bottom point, f of A is the smallest. F of A is less equal to f of x in that given interval. So this is the minimum value basically in that particular interval from x1 to x2. Also, graphically speaking, you have a changing from to decreasing to increasing. If the function changes from decreasing to increasing, at that particular change point, that's what we call a relative minimum. So relative minimum occurs when function or graph changes from decreasing to increasing. Similarly, for relative maximum, the function increases all the way to the top, to the heel, and going back down, then we call this a relative maximum. So here is relative maximum, value is the relative minimum. And you can look at it from the increasing, decreasing intervals. Okay, so now let's look at this. First one, right here you have relative minimum because it's decreasing all the way to the bottom and then start to increase. Okay, that's why we have relative minimum here. So because it's decreasing, change from decreasing to this part is increasing. Now our second part, we have increasing all the way to the top. It's increasing all the way to the heel, and go back down. Again, we get decreasing here. Then we have relative maximum. Then back down here, decreasing all the way to the bottom and increasing a relative minimum here. One more time, increasing all the way to the heel and go back down, relative maximum. So by labeling those increasing, decreasing intervals will help you find those and locate those relative minimum and relative maximum. Now let's take a look at the average rate of change. Average rate of change is also called the slope of the secant line. It's the same thing as saying slope of the secant line. Secant line is a very important concept to understand the calculus. So this is like the foundation for calculus courses. So we learned that slope of a line could be interpreted as rate of change. You basically rate of change in changing y over changing x. We also call that vertical change over horizontal change. Okay, so this is very intuitive interpretation of the slope. And slope of secant line could be interpreted in a very similar fashion. Okay, so for nonlinear graph, every change from x1, f of x1 to x2 and f of x2, we could just use changing y, which is vertical change right here over the horizontal change. Okay, so vertical change is expressed as f of x2 minus f of x1. Horizontal change will be the x2 minus x1. And this is how we call this secant line, right? Secant line between those 2 points. We can use this symbol M with a subscript SEC. SEC means secant line. So every change of the f from x point x equal to x1 to x equal to x2, basically f of x2 minus f of x1 over x2 minus x1. Changing y over changing x. Exactly the definition of the slope. And that's how we find the slope of the secant line. And then let's find the average rate of change of f of x equal to x cubed minus 3x from a couple different scenarios. So we want to find out the slope for this line right here and also for this line. So for first line, in order to find slope, we need to know what is, we know x1, x2. Also need to know what is f of x2. F of x2 is the same thing as f of -1. So we go back to the function and replace x with a -1. So we get -1 cubed minus 3 times x. 3 times -1. -1 cubed is -1. -3 times -1, positive 3. So get positive 2. Yes. F of x1. That's gonna be f of -2. So again, replace x with a -2. We get -2 cubed minus 3 times -2. -2 cubed is -8. Adding 6 turns out to be -2. Now once we know this, secant line m secant equal to f of x2, y2, right? This is the same thing as y2 minus y1. F of x1 is y1 over x2 minus x1. I'm just throwing all the numbers, so we get a 2 minus -2 over -1 minus -2. 2 minus -2 turn out to be 2 plus 2, that's 4. Minus 1 plus 2 is 2 negative turned into positive. That becomes positive 1. So 4 over 1 turn out to be 4. So if you go back, slope here for the first secant line right here, it's going to be positive 4. Okay, as you can see, it also matches the positive, increasing pretty rapidly, and slope turned out to be 4. As second are very similar, we just have to find out what is f of 1, and we can easily find f of 1. Okay, f of 1, again plug into that, x cubed. So it's 1 cubed minus 3 times 1. Still, we're dealing with the same function. So it's 1 minus 3 turn out to be -2. Okay. F of 0, it's 0 cubed minus 3 times 0. That turn out to be 0. And you just plug it in. And similarly, we end up with a -2 as a slope of secant line. And if we go back really quickly, you see this is a decreasing line. So slope of secant line turned out to be -2. Okay. And the last topic is about even R functions. So for even functions, by just algebraically speaking, we come up with f of -x. If f of -x is something as f of x, then it's an even function. If f of negative x equal to negative f of x, then it's R function. So we just need to do some algebraic transformation, and an even function symmetry with respect to the y-axis, because with the different opposite x values, y values are the same. That means symmetry with respect to the y-axis. And the R function symmetry with respect to the origin. Because x becomes negative x, y value becomes negative y. That's exactly the symmetry with respect to origin. Now, let's take a look at g of x equal to x cubed and minus x. Let's determine whether it's even or R function. So the most important thing, determine what is g of negative x. Now we'll just go back to the function, replace x with negative x. So we get negative x cubed minus negative x. Simplify, we're going to get negative x cubed, adding x. Okay. Combine the sign and get that. And if you factor out this negative out, then you're going to get negative x cubed minus x. And we know this is x cubed minus x g of x. So g of negative x equal to g of x, negative g of x. And according to the definition of the R function, this is definitely R function. So we determine this is R function. Alright, now let's take a look at another function, h of x equal to x squared plus 1. So now most important, determine what is h of negative x. Replace x with negative x in the original function, negative x squared adding 1. So negative x squared becomes positive x squared adding 1. And this is exactly the h of x. And that being said, h of negative x equal to h of x. So that tells us it's definitely an even function. Okay, so again, we're using the definition, determine even R functions. And as you can see, graphically speaking, for the R function, it's symmetry with respect to the origin. Because of any point here, x becomes negative x, y value becomes negative y. Okay, they both become opposite, so that's why symmetry with respect to origin. And this is for R functions. For even functions, since y value are the same, but the x value are opposite, so this is exactly a symmetry with respect to the y-axis. And that's how you utilize the graph to help understand the even R functions and relate it to the symmetry. Okay, that's pretty much it.